gotta calm down. All right, we did it. Okay. So this talk is called Compacting GC for MRI. Hello, everybody. Hello. My name is Aaron Patterson. I'm also known as Tenderlove, and if you don't recognize me in person, this is what I look like on the internet. That is my icon. So this is me. This is my online me, but this is my real me. This is me in real life. And I have two cats, and this is one of them, Gorbachev. This is Gorbachev Puff Puff Thunderhorse the third. And I think that some of you may not know him because I was airdropping him to people, and some people declined them. So maybe now you know where this was coming from. This is my other cat, SeaTac Airport, Facebook, YouTube, Instagram, Snapchat is her full name. But we just call her Choo Choo. And I have stickers of my cat, so if you would like a sticker of my cat, come say hello to me. Like, I'm a pretty, shy person, and I know other people are too, and I have a hard time making conversations. So if you want to come say hi to me, I'll have stickers, and we can talk about cats. So that is something we can do together. I work for a small startup company called GitHub. I don't know if you have heard of GitHub, but it's a place where you can host code online. You could say that working at GitHub is my active job. All right, okay. I'm really excited to be here in Bulgaria. This is my very first time ever here, and it's amazing. I'm having a really great time. The food is amazing, the people are so friendly, and I just want to say thank you so much for having me here. Whenever I go somewhere, I like to support local stuff, like try out the local foods and do things that local people do. So I tried out some local drinks. I can't read this, but I had this, and it was interesting. I also tried out rakia, and the photos are missing of this. It was very good though. I did enjoy that. I also wanted to check out local computers. I thought it was cool to try some local computers, so I tried out one of these. And as mentioned when I was being introduced, I also wanted to get some local cultures. So I got this. It is Bulgarian yogurt culture. So I'm bringing Bulgarian culture home with me. So thank you so much for that. I didn't know how famous Bulgarian yogurt was until I told a friend of mine that, hey, I'm going to Bulgaria. My friend, she's in Japan, and she said, oh, yogurt, and I'm like, what are you talking about? And she's like, yogurt, they're famous for yogurt. I'm like, well, I have no idea what you're talking about, but the most famous yogurt in Japan is called Bulgarian yogurt. Like, it says Bulgarian yogurt on it, so that's how I learned about it. Anyway, I'm on the Ruby core team. We're the team responsible for doing Ruby development. I actually recently found out that I've been on the team for almost 10 years. In October, this will be my 10th year on the team. That's my very first commit. Oh, thank you. I am also on the Rails core team, and I looked up my oldest commit on Ruby. Let's see my oldest commit on Rails. This is my very first commit. It was in 2009 too. It was merged by Jeremy, but I wasn't on the Rails core team until 2011. So I've been on the Rails core team for 8 years. And I'm not bringing this stuff up to just say I've been doing this for a long time, I'm great, but I actually wanted to talk about why I got involved in the community and why I've been in the community for so long. And the reason is that I love Ruby. I love the Ruby programming language. I've actually been doing development work since 1999, and I got into Ruby programming around 2005 because somebody went to the No Fluff Just Stuff conference, someone at work, and Dave Thomas was giving a presentation about Ruby, and they brought it back to work and told me about it, and I tried it out, and I thought it was amazing. At the time, I was actually a reluctant Java programmer. I used to be a Perl programmer, and then I was forced to switch to Java, and I thought for sure, once Perl 6 comes out, I won't have to deal with this Java crap anymore. Perl 6 will save me. Well, we know how that ended up. That is not how that happened. I learned about Ruby, and it felt like a breath of fresh air to me as a Java developer. Like, everything was so easy for me. Everything just worked the way that I thought it would work. When I made a mistake, it was easy to tell why. Everything was, like, the language was very easy to pick up. There was no boilerplate code, and I want to show you what I mean by boilerplate code. So I went and looked up Java. At the time, I was doing Java 1.3, so I looked up how do you do, like, map in Java 1.3. And I'll give you an example here. Here we have a list. We're just iterating over a list of strings and trying to convert them into integers. On the left is the Java example, like similar to what I would have written at the time, and on the right is our Ruby example. And what's really actually annoying about this example is I think the Java example doesn't actually work, because right here it returns an int, which is not an object, and you can't just put that onto an array list. So this doesn't actually work. You have to think about primitive types versus object types. And in Ruby, we don't have to think about that stuff because everything is just an object, and it lowers the amount of mental overhead required for doing programming in Ruby. And I am like a very forgetful person, so lowering mental overhead is like very important to me. Anyway, so I want to talk a little bit about my very first serious Ruby program. In 2005, they released the third Lord of the Rings movie, and I wanted to see that. I wanted to see that movie. They were releasing the third one, and it was going to be on my birthday in December 16th, 2005. They were releasing the third one. All three movies were going to be played on the same day, and I wanted to go see this. So I went to the website. You could buy the tickets online, but the website kept crashing. Now, I was at work, and our application, it took 10 minutes to compile the application, so every time I made a change, I'd have to wait 10 minutes. So what I decided to do was, during that 10-minute time period, I would write a Ruby program that would go and try to purchase the tickets for me. And I even put my credit card number into a Ruby program that's submitted to a website. Now, the problem was it would submit the form, but I knew what the error page looked like. I knew that there was an error, but I didn't know what the success page looked like. So what I decided to do was if there was an error, it would retry, and if the page changed, it would log a message and then retry. And I let the program run, and I forgot about it. And then I noticed in the terminal, the output had changed, and I was like, oh, the output changed. Oh, I wonder what's happening. So I went through the process in my browser and discovered that it was actually succeeding over and over again. And I had a little small panic attack, and I called the credit card company, and I asked a really shady question. I was like, "Hi, how many times have I charged my credit card today?" And they said to me, "Oh, you charge your credit card once." And I was like, "Oh, good, okay, good." And then I called the ticketing company because I wasn't sure if they had actually gotten a ticket for it had actually worked. And I gave them my details, and they're like, "Oh yeah, you purchased 2 tickets. But it looks like we've tried to charge your credit card hundreds of times." And I was like, "Oh, yeah, I was just hitting refresh. I don't know." So the moral of this story is never write infinite loops. You should have an exit case. Now the other thing is that I really love Rails. At the same time, around this time is when DHH published that whoops video. So I discovered Rails at the same time, and it had exactly the same features as Ruby. It was so easy to use. Everything just worked the way that I thought it would work. I didn't have to write any boilerplate code, but it was a bit more than just these specific traits. easy to use stuff and no boilerplate. Those are specific traits about Ruby and Rails, but what I really enjoyed was actually that the community valued these particular things. The values of the community, it really resonated with me, and those values were that we don't want to put up with like writing a whole bunch of, like we don't want to write XML configuration files or wait long times for compilation. We just want we want the burden to be on the computer, not on us, the programmer, and that made me feel really good. It was probably the first time that I had actually enjoyed programming, like had a good time. And I thought to myself, like, I need to do this as my day job. This is what I want to do. And you have to remember this is in 2005, 2006, and I thought I must write Rails. This is actually a picture of me from 2006. I looked this up. Unfortunately, at that time, nobody was hiring Rails developers because it was so new. Like there were no companies doing this. But I really, really wanted to do it, and I ended up joining a startup with some of my coworkers quit their job to start a startup, and they decided to do it in Rails, and I went along to work with them. But unfortunately, since nobody was hiring Rails developers, I had to take a salary cut, and that salary cut was the tune of 25%. So that was like a lot of money going away. That was not good, but at the time, it actually really motivated me to get involved with the Ruby and Rails communities, and the reason I wanted to do that is because I wanted to improve the language and improve the framework such that we would have more companies doing, like, developing Rails applications, so that I could go work somewhere else and maybe get a raise. I wanted more people involved in the community as well, so that we could increase the number of companies, but also I wanted other people to be able to feel that productivity boost and that feeling of, oh, the computer should be doing the work for me, not me. Like I don't want to do that. The machine will do that. I wanted other people to have that feeling too. Now, what I'm really trying to say here is, why is my thing advancing on its own? Anyway, this is essentially a very long-winded way for me to say, like, thank you to all of you for being Ruby and Rails developers. You're the ones creating companies and creating jobs and making it, like, writing Ruby code so that I can also write Ruby code during my day job. So if it weren't for you writing Ruby code and Rails code, I don't think I would be able to have the job that I have today and be able to write in the language I love so much. So thank you, all of you. And now we will go on to the actual technical part of my presentation. I'm going to talk to you, I want to talk to you today about compacting GC for MRI, and this is a feature that I wrote for Ruby, and it's going to be shipping with Ruby 2.7. And this feature is, it took me 3 years to do this. To be honest, this presentation is about the most difficult code I've ever written in my entire life. And I feel weird that I'm like summarizing it here for you in like a 40-minute presentation or something. But I am going to explain it, and I hope that I will do a good job of that. Anyway, 3 years. It took me 3 years to do this, and I'm going to describe to you like what it is exactly, the algorithms behind it, how it works, and how it's beneficial to all of us. So first off, stop advancing. What is compaction? Compaction is essentially taking allocated memory, like say we have some memory like this in our computer, and rearranging it such that the free memory and the allocated memory are next to each other, like this. All we're doing is taking that free stuff, the free chunks and the allocated chunks, and trying to join them together so that they're grouped together like this. And maybe some of you remember something like this. Defragging your hard drive. This is exactly what we're doing, except that rather than defragging a hard disk, we're defragging the memory inside of the computer. So yeah, look at this and feel nostalgic. So why bother doing this? What are the benefits of compaction? Some of the benefits include like efficient memory usage. So for example, let's say we have a memory layout that looks something like this, and we need to allocate something new. And we're going to allocate something that's about this wide. It's as wide as that box there at the bottom, but unfortunately, that box doesn't fit inside of the free slot. It's too wide for that one, and it's too wide for this other one. It won't fit in that location either, but if we were to rearrange all of these, then it could actually fit inside of this free memory, and now we can actually allocate into that location. So we're now able to, before we had essentially run out of memory, but now we're able to actually allocate more stuff and use our memory more efficiently. Another advantage of compaction is that we can make efficient use of CPU caches. And the way this works is when we have a program, the program has to read memory and execute stuff based on the memory that it's read. And when your program asks the CPU to go read some memory, the CPU actually reads that memory in chunks. So when you say, like, I need to access, maybe 50 bytes of data or some number, the CPU doesn't actually get 50 bytes, it gets more. It gets enough to fit inside of a cache. So the CPU will go ahead and read some chunk into a CPU cache, and as your program is processing that, you want to be accessing the data out of that CPU cache because it's much faster than accessing the main memory. So let's say your program is going along, executing, it read this memory, it's all in the CPU cache, it's going along, processing, but all of a sudden, oh, now we're processing free memory, that's not what we wanted, we actually need to go to a different chunk and read that chunk in. So the program does that, it asks the CPU for a different chunk, so it'll go do a second read and then continue processing the program. Now, reading from this different location takes time, so we want to try to reduce the number of times that we have to go move around, like read different chunks out of memory. So if we were to rearrange the heap so that it was compacted like this, then when we read memory, we can take full advantage of the CPU cache. We can read through all of it and not have to move around to read multiple chunks. Now this particular thing this particular phenomenon is called good locality. We say that we have good cache locality. We're able to load data into the CPU cache and take full advantage of that CPU cache. Another example of why compaction is good is copy on write friendliness. At work, we use the Unicorn web server, and it saves memory by using a copy on write technique, but compaction can actually increase the efficiency of this particular technique. Now, what copy on write is let's say we have a parent process, and that parent process forks a child process. Now, when you fork a child process, that child process doesn't actually make an exact copy of what the parent process has. It creates a virtual page, and that virtual page points back at the parent process like this. So we don't actually double it, we just have something that looks like it's doubled. Now, what happens is, if the child writes to any of this memory, come on, slides, write to the memory, it will actually sever that connection and copy down to the child process before writing to that section. So let's say we want to write to this free memory. The operating system will sever that connection, copy it down, and then we write to it. Now, unfortunately, this technique, when you write to a particular chunk, the operating system doesn't just copy that one little section that you wanted to write to. It actually copies in page sizes, which are about 4K, and that can be larger than what you actually wanted. So if we are able to compact this heap, we decrease the probability that we're going to be writing into these free slots and copying too much memory down to the child process. So this is a third way that compaction can help us out. And all of these problems are essentially caused by having fragmentation in your memory, and compaction is just a process of eliminating this fragmentation. So compaction is the solution for fixing a fragmented heap. So when I say fragmented memory, just to reiterate, what that means is we have all these, you're going too many times, clicker, I will stop using this. Fragmented memory essentially means that we have these chunks of free space interspersed in our memory, and it's fragmented, and when we compact it, we eliminate that fragmentation by moving all the same types next to each other. Now, before we get into the actual algorithms implemented here, I want to talk about the two heaps that we have in our Ruby programs. So we can say our program has actually two heaps, and if we were to visualize this, for example, this is our system memory. We just have some amount of memory in our entire system. Then when we allocate memory, we use malloc. It's a system call to allocate memory from the ask the operating system for memory. So we can think of that as our malloc heap. So that's all the memory allocated with malloc. Now inside of that malloc heap, we have a secondary heap, which is Ruby's object heap. It lives inside of the malloc heap. So Ruby's object heap is allocated with malloc, and it lives inside of this heap. So we can kind of think that we have two different ones, but they're somewhat related. Now, every time we allocate a new Ruby object, it comes out of Ruby's object heap. So for example, let's say we say, I do object.new. If you do object.new, it comes out of Ruby's object heap. Now, ideally, Ruby's object heap would be exactly the same size as the malloc heap. There would be no difference between those two. But unfortunately, that's not the way that it works today. And I'll give you a simple example of why that is. Let's say we allocate a string. When you do a new string, we allocate the Ruby object for representing that string out of Ruby's object heap, but the actual character buffer for that string is contained inside of the malloc heap. So our Ruby string object points into the malloc heap. So this is why the malloc heap will be larger than Ruby's object heap, is because we have to point to that malloc data. Now, the reason I'm explaining this is because memory fragmentation can occur in both of these heaps. It can occur inside of this malloc heap, and it can also occur inside of our Ruby object heap. What we do at work for dealing with this in the malloc heap is we use jemalloc. It works well for the malloc heap, or you can use some other malloc implementation like tcmalloc. Now, for dealing with fragmentation inside of the Ruby heap, we use gc.compact, and that's the subject of the presentation today. This is the patch that I wrote and what we're going to talk about. So let's talk a bit about Ruby's heap. We're going to take a look at Ruby's heap, and that's not the system memory or the malloc heap. It's the Ruby object heap that's stored inside of that malloc heap. Ruby's heap looks a little bit something like this. Ruby objects are represented by a fixed amount of memory. Each object is 40 bytes wide, and we can call these 40-byte chunks a slot. Each slot can be empty or filled, so it'll either have something in it or it won't. And later I'm going to introduce a new type, so we either have an object or we don't have an object. Later we're going to introduce a new color, a new type, that is moved, so we'll have a third type later. These slots are stored on a contiguous chunk of memory, and this contiguous chunk of memory is called a page. And each page is about 16 kilobytes wide. Now, our entire heap is made out of multiple pages, so we allocate multiple pages, and each of these pages are allocated with malloc. So we use the malloc system call to actually allocate each of these pages. Now, each slot inside of this heap has a unique address. So all of them have some number associated with them, and that number is unique and fixed. So let's take a look at the actual algorithm for doing compaction. The algorithm that I implemented is one called two-finger compaction, and this originates from Lisp. It was originally published in this Lisp programming language in 1964. And essentially it has two steps. One is to move the objects, and the other one is to update the references. First, we're going to be looking at how the objects move, and then we'll look at updating the references later. So let's say we have a heap layout that looks like this. We have 6 objects, A, B, C, D, E, and F, and each of those are located at fixed addresses. So they all have their own unique address. The way this algorithm works is it points 2 fingers on either side of the heap. We have one finger called a free slot, or a free pointer, and the other one called a scan pointer. And the way the algorithm works is that the free pointer moves to the right until it finds a free slot, and then the scan pointer moves to the left until it finds a filled slot. And once they find those locations, it swaps them. So F moves over to 4, and then we leave a forwarding address. So we say whatever was here in slot 9, it is now at slot 4. Then we just move the free pointer until we find a free slot, the scan pointer until we find a filled slot, do the swap, leave a forwarding address, and we repeat this process until the two meet. So once those 2 pointers meet, we've finished moving all of the objects. After that, we need to update references. So let's say we have this same layout, but they have a relationship like this. Maybe A points at D and B points at F. After we've moved all of the objects, the references remain, but they're incorrect. So we have to update those references. And the way that we do that is we essentially just look at each object and say, hey, what references do you have? Well, you used to point at, let's see, A points at D, which is fine. We don't need to update it. It didn't move. B points at 9, and whatever was in 9 is now at 4, so we need to change it to point at 4, so we do that. Then C points at 8, but it moved to 5, so we need to update that. So we just update. And then we just repeat this process for all of the objects in the heap until it's done. Yay, I think it's actually done now. I don't know why I animated this. Just to show you, it has to do that. So once we're done updating all of the references, we just turn these moved locations back into free slots, and now we've completed the process. We've compacted our heap. So if we were to look at this object movement code in Ruby, it might look something like this, where each of these sections, you don't need to read the code, I'm just going to point out the major parts of it. First, we have to check to see whether or not those pointers have met. If they haven't, we go through the process of moving and forwarding, so we copy and forward, and if we first, we check to see if the pointers have met, then we copy and leave a forwarding address, then we advance the free pointer, and then we retreat the scan pointer, and we just repeat this process. So this is essentially what it is in Ruby code, though I wrote it in C. It's easier to read in Ruby. Well, this isn't that easy to read, but I think it's much easier than the C code. So for the reference updating step, essentially it looks like this. All we do is iterate over each object in the heap, looking at the references and updating those references. So whether or not, if it's moved, then we just set the new location. Now, when we look at this code, updating references looks like it's much easier than doing actually doing object movement, but really this is the hardest part of the entire process. This code right here is hiding a whole lot of complexity, and it's right here that the complexity is hidden. How are references actually stored for a particular object? We have to be able to find all of them and update them. So for example, how do hashes hold references? How do arrays hold references? How do objects hold references? Et cetera, et cetera, et cetera. How do all types of objects hold references in Ruby? We need to know that and then be able to update them. Now, I'm going to show you we're not going to go through each of those types, but I'm going to show you the actual code that I wrote for this. Here is the C code. Hold on. This is just the reference updating part of this feature. That is it. I didn't count it, but I estimate that doing reference updating was approximately 80% of the patch. That's about what I think it is. So let's take a look at, since this is so complicated, let's take a look at, I want to talk a bit more about reference updating. Specifically, I want to talk about supporting C extensions. One blocker for doing heap compaction is that we need to be able to support C extensions. If objects move out from underneath the C extensions, then those C extensions will crash, and we need to make sure that that doesn't happen. And I'm going to show you a scheme that I came up with for preventing that happening. And I don't think anybody has come up with this scheme before, so I think it is a novel technique. People have said it is novel. So we have to be able to know where references are stored. This is the most difficult problem about this, about updating references. So for example, if we wanted to update an array, you and I, today we are all Ruby core contributors. You and I know how an array works because we can go look at the source code and read it. We know how an array stores its references. We know that an array just stores a pointer to a value buffer, and that value buffer holds pointers to some other Ruby objects. And when the compactor runs, since we all know how arrays are implemented, we all know how to update the references for an array. Now, we have the same sort of situation with hashes. Since we all know how hashes are implemented because we can read the source code, we know how to update hashes when the garbage collector runs or when the compactor runs. And we can know this, we can know the internals for all the different types of classes. Like we know that how strings hold references, classes, modules, symbols, etc. And it may be it's a lot of busy work going through and reading all of those implementations, but we can know it because we can read the source code. So the GC, when the compactor runs, it can update all of these known types. Now, we can define known types as types that are implemented by Ruby, not in Ruby, but by Ruby in C. But we know about these types. So we have to ask, what are unknown types? And unknown types, I call unknown types as types implemented in C. So I'm going to give you an example. At work, we use a library called YAGL. It's a JSON parser. And this is the struct that backs the parser. And if we read the struct closely, we can see that this struct can hold references to two Ruby objects. Builder stack, I don't know what they're for, but it can hold references to two of them. So when we allocate a new YAGL parser, we use malloc to allocate this struct. Then we create a Ruby object out of the Ruby object heap, and this Ruby object is of type T data, and it points at that malloc memory. That malloc memory contains two references to two different objects. Now, we don't need to know what types those two different objects are, we just need to know that there are references there. So, since the GC doesn't know anything about the YAGL parser implementation, it doesn't know how to update any of these references. So if the compactor decides to move one of these references, the struct could point at a wrong location, and if that happens, say we moved it to a different location, the whole program will crash. So how do we prevent this type of crash? And the way that I came up with to prevent this type of crash is essentially this YAGL parser, it has to call a mark function on these objects, otherwise the objects will get garbage collected and go away. It has to call rbgc mark, and that's the actual source code there. It's calling rbgc mark and it's passing the objects into mark. So we can say like, okay, anything that's passed to rbgc mark, we just won't allow it to move. So we don't allow those to move because you called rbgc mark and gave it that object. So anything marked with rbgc mark cannot move. That is the rule. So the way I implemented this is I introduced something called pinning bits. It's essentially just a bit table. So for example, let's say we have this YAGL example here, this JSON example. During the mark phase of the GC, YAGL will use rbgc mark to mark its references, and when that happens, we can set a pin bit for the object. So we have this pin bit table here, and when YAGL calls mark, calls rbgc mark on those, and we pin those two bits. We set a flag saying these two objects cannot move. So when the array marks its references, it uses rbgc mark, or it uses gc mark no pin. So we mark it, but we don't pin it. So there's a difference between the YAGL implementation and an array, Ruby array internals implementation. Then during our move step, we do the same thing as normal, except that when the scan pointer encounters a filled object, it says, oh, that pin bit is set, so I'll just move on to the next one. And the compaction algorithm runs just as normal. So we'll do the same thing, yay, fancy. Did it. All right, so we don't know, the GC doesn't know how to update those references for YAGL, but it doesn't need to because we have guaranteed that none of those references have moved. Now, during reference update, we don't know how to update references for YAGL, but it doesn't matter. We do know how to update references for the array, so we update them, and then we just continue everything as normal. Yay. Keynote animations. Woo. All right, so known types, internal types to Ruby, use GC mark no pin, whereas unknown types, this is a private function, whereas unknown types use rbgc mark. And this is the way that we solve the C extension problem. So there's one other thing that I added, which is allowing movement in C extensions. So let's say we want to have a C extension, but we want to support compaction as well. And in order to support this, I introduced 3 new concepts: compaction callback, no pin marking, and a new location function. So as we said earlier, the GC can't update a C extension because it doesn't know its internals, but a C extension can update itself. So we're going to walk through the steps here of how to fix the YAGL parser so that it can support compaction. So before compaction support, we register a mark and a free callback like this. In order to support compaction, we just register one more. So we've got our mark callback and our sweep callback. In order to support compaction, all we do is we add a new callback here. So we have a YAGL parser compact function. So this callback gets called every time the GC does a compaction step. So now we need to define that function. During the mark phase, we introduce this. We say, okay, we're going to call, instead of calling RBGC mark, we'll now call RBGC mark no pin. So we're saying we have a reference, but we don't want you to pin it. Then inside of our compaction callback, we update our references, and we do that by asking the GC, hey, where is the new location? If this object is moved, please tell me where the new location of this object is. So if the object hasn't moved, it returns the original address of the object. So these are all the steps required to give YAGL, to make it so that YAGL can support GC compaction. So there is one known issue, and this is kind of an annoying issue. So let's imagine we have 3 Ruby objects like this. One implemented in Ruby, one implemented in C, and it doesn't matter how the third one is implemented. So we have a Ruby object pointing at something and a C object pointing at another. And imagine you are a C extension author and you know that this Ruby object is holding a reference to this third object. So you're not going to mark it. You know that the Ruby object is marking it for me. So we say, okay, this thing is automatically marked by Ruby, so I'm not going to mark it. It's not marked in C, not marked here. This type of reference, I call this it's a hidden reference, because the GC doesn't know that this relationship exists. It only knows about one of these relationships. Now, unfortunately, what will happen during compaction, since it doesn't know that that secondary or that hidden relationship exists, it says, oh, okay, I marked this, but I didn't pin it, so I can move it because it just belongs to an array, so I'll move it. And then when I update references, the array reference gets updated correctly, but the C extension, that C object, it doesn't get updated at all because it doesn't know that relationship exists. So then our program will crash. I didn't do the flame thing. Come on. Did I do the flame? Yes. Our program crashes. Now, I don't think that this is very common. This type of relationship may not be very common, but I did find it in 3 places so far. The first place I found it was internal to Ruby inside of Ruby's virtual machine instructions. Essentially what happens is any literals in your Ruby code, those are actually all allocated as Ruby objects. So that string bar is allocated as a Ruby object and a Ruby string object. And when your code executes, it just copies the Ruby object. So that's how we have how that code is actually implemented. Now, the way that this worked is that when your code was compiled, those literals would get added to a thing called a mark array. And the virtual machine relied on that mark array to ensure that all of your literals stayed alive. So this reference down here at the bottom was not marked. So it essentially relied on that array to, I guess, indirectly mark all of those objects. So I changed this in Ruby 2.6 to eliminate that mark array so that basically the instruction sequences just mark things directly. I call it direct marking, and you can look up the patch there. But the upside of this is it works with, it eliminates the mark array completely, so it decreases the amount of memory that your programs use, but it's also compaction friendly. So we're able to essentially kill 2 birds with 1 stone here. So that was nice. Another issue where I found this was in the JSON gem. Essentially this same type of issue was occurring. We have Ruby, this exact same setup, except that we have so the reference was made using Ruby code, and I was able to write pure Ruby code that would actually cut this reference. So I could write a pure Ruby program that would kill this, because I know that it's a Ruby program. The garbage collector would actually say, oh, okay, there's no reference anymore, so I will just get rid of this object. It would get rid of it, and then the C implementation was pointing at nothing, and this whole thing would crash. So I'll show you the problem code specifically. It looks like this, where they would say, okay, I'm going to go get a constant, and I'm going to assign that to a global variable. So it would say, give me this constant, I will assign it to a global variable. And the way that I could make this crash is I would say, okay, I know you assign this to a global variable, so in Ruby, I'm going to remove the constant, and then do a GC, and then I'm cutting this reference right here with pure Ruby code, and that will cause the program to crash. So it can no longer, that reference to the nan constant went bad and the program will crash. Now the good news is that the fix is very easy. All we had to do is say, okay, you're fetching this constant, we'll mark it. Say it needs to be marked when the GC runs. I also found this in the message pack gem when experimenting, exactly the same type of situation where I could cut the reference using Ruby. The object would go away, and then the program would crash. Now, my theory behind this is that you should be able to write any Ruby program, and a pure Ruby program should not ever crash, so we should treat this as a bug. And I was able to file a ticket with the message pack authors and say, hey, I'm able to write this Ruby program. It's a very strange Ruby program. I admit it does not look very good, but I can make your extension crash. So we should treat this as a bug and fix it. So what this boils down to is it means that we can define a very, very simple rule, and that rule is if you hold a reference to something, you must mark the reference. Now, the other alternative is just write all of your code in Ruby, never write any C code. That is my pro tip to you. Do not write C code. I will write C code so that you don't have to, please. So I want to talk about one more challenge, and that's the object ID. Now, in general, directly accessing memory prevents objects from being able to move. So all of those examples that we saw previously were examples of direct access to memory, and that direct access messing things up. One thing that actually accesses memory directly, though you may not know it, is the object ID method. Now, object ID methods are based on the object ID is based on the location of your Ruby object in memory. So, for example, in this case, since that first one is located at position 1, the object ID will be 1. Now, unfortunately, what this means for a compactor is if the object moves, what should the ID be? Should that ID have been 9 where it previously was, or should it be 3, the new location? So in order to handle this situation, what I said is, well, okay, the object ID of an object depends on when you call the method. So here's an example. Let's say we call object.new, then we run gccompact, and then we check the object ID. So the way this program will run is we'll create a new object. It gets put into slot 4. We compact the heap. It moves to slot 1. Then we check the object ID. In this case, the object ID is 1. Because you never knew it was in slot 4, so it doesn't really matter. When we read the object ID is 1. Now let's make it a little more complicated. We'll create a new object, check the object ID, compact the heap, and then check the object ID again. So in this case, we'll allocate into 4. Now we'll check the object ID, and in this case, it should be 4, because we're at slot 4. Now, if we compact the heap, maybe the object moves around, but what happens here? What should the object ID be? We can't change it. It needs to be 4 still. Otherwise, it would be very strange. You would not expect this to return a different value. So in order to support this case, I created basically a global map of what I call scene object IDs. So this is what the object ID implementation looks like if it was written in Ruby. Essentially what we say is, okay, the first time you access the object ID, we'll look at your location in memory, and then we'll cache that value. Then when the GC runs, we can update that table. So the table will look something like this. We create a new object, check the ID, we compact the heap. During heap compaction, we update and we say, okay, that object ID that was at 4, it's now at 1. Then when we look it up again, we can look it up in the map and say, okay, the value is 4, so we return 4. Now there's something even a little bit more complicated. Let's say we do this. We create a new object ID. We swap the new objects. Check it again. It should be 4. But what happens if we create another object and that object is allocated into slot 4? What should its object ID be? It can't be 4 because we already have a 4. So what should that value be? In this case, I call this a collision. And essentially what it does is we say, OK, if this object has been seen before, we'll just increment the ID by 1 and search until we can find an object ID that's never been used. So in this case, we'll go through here, do the same process. We get a 4. Yay, arrow. Go. So we get a new slot in 4, and we say, well, 4 is already used, so we're just going to increment by 1, and we get a 5. Now, the last thing we have to do is we have to clean up this hash when objects get freed, because we need to be able to reuse those object IDs. So during GC, we'll just delete from that hash when objects go away. Now, the moral of this story is, please don't use object ID, because this is a huge pain for me. No, go ahead and use object ID. It's fine. Don't worry about it. Don't run out and change your code. Just, you probably shouldn't be using it in production. I think it might be a code smell if you're using this in production. Though I have to admit that we do use it in production, and I am trying to fix our code not to do that. So let's take a look at the actual impact of this patch. Here's the heap of a basic Rails application. This is a graph of your heap. Now, red squares in this, you might not be able to see it very well, but there are red dots in here. And those red dots, they represent slots that are pinned and cannot move. The black squares represent slots that aren't pinned. There is an object there, and they can move. And the white dots, those are free spaces. Each column of this is a page, like we discussed earlier in the presentation. So each column is a page, and each square is a slot. And we've lined up all the columns here. So you can see there's a lot of white space in there, so we can say that this heap is very fragmented. So after we run the compactor, our heap actually looks like this. So you can see that we're able to clear up a whole bunch of space in there. We're able to say, it's kind of hard to tell between these two, but you can see that clearly we have fewer white dots, and it actually got skinnier. So we were able to save memory there. Now I want to show you, this is just a basic test Rails application. I'm going to show you github.com. This is our Rails application. The top is before compaction and the bottom is after compaction, but the amount of memory we use, this is our heap after we boot the application but before we start accepting requests. The heap is very large, but you can see an impact, and I'm going to show you here. This is not the whole thing. This is that is the whole thing. So you can see that it is impacted, and we allocate a lot of memory. So future plans of this, I want to do some performance improvements. Currently, the compactor is very, very inefficient. It requires 4 steps. We have to do a full GC. It moves all the objects. It updates all the references, and then it does a full GC again. I think that we can reduce this to at least 3, doing a full GC, moving objects, and updating references. And maybe we can even get it down to just two steps. So I want to work on efficiency. But since you have to call the method specifically, it's not going to slow down your Ruby programs. The way that we use it at work is we say, OK, boot up the app, compact the heap, fork all of our children, and then just continue on with our lives. So it doesn't impact the runtime of our application. Though I do want to make this automatic in the future, so you never have to call that method. And in order to make it automatic, obviously we need to improve the performance. The other thing I want to do is change to sliding compaction. Essentially, like right now, the current compactor uses the 2-finger algorithm we talked about, but I would like to change that algorithm to a sliding compactor. And essentially, the way that works is it just takes everything and pushes it over to one side like that, rather than doing the swap. And the reason I want to do that is because it actually produces better locality. The 2-finger algorithm results in an object layout where everything is placed scattered randomly throughout your heap. The 2-finger compactor actually makes sure that all of your objects are in the same same place. They're moved, but they're in the same place relative to each other, and that is actually better for CPU caches. The other important thing about sliding compactor is that it supports variable width allocation. As we said earlier, all Ruby objects are only 40 bytes wide, but what would be very nice is if we could actually take strings and allocate them next to the Ruby objects themselves. That would give us even better cache locality. So beyond this, so supporting variable width allocation would be really great, because another thing I would like to add is actually variable width allocation. This would completely eliminate the need for things like JE-malloc or other malloc implementations, because we would be in control of all of the memory that's being allocated. So those are my long-term plans for this. And actually, that is it. Thank you so much. You can see the issue here along with a description of all the stuff that I talked about, and I really, really want to say thank you. It's been an honor to be here. I really appreciate it. So come say hi to me. I will be at the party later, and I will have stickers too. Thank you.